This brief video is going to look at the MATLAB files provided to support learning of Laplace transforms, partial fractions and poles. Laplace transforms then are introduced in chapter 1 of the main textbook. Chapter 1 is there, but it's used as a tool throughout all the other chapters. So defining and using Laplace by hand is tedious. We don't want to do it by hand. So here we're going to show how MATLAB can be used to improve efficiency and probably accuracy too. This means the user can then focus on insight and application rather than pen and paper calculations. Some definitions first then. So there's the definition of a Laplace transform, which you're probably all familiar with, and an example in the yellow box. And similarly, inverse Laplace, you'll notice we normally do using a lookup table. So we have a number of transforms that we already know and we identify which match. Core skills you're going to need are interpretation of Laplace transforms, especially for higher order transforms where it might not be obvious. And this also means you've got to be good at partial fractions because these allow us to expose core dynamics. What MATLAB files do we have then to support Laplace transforms? Now we're going to assume you've downloaded the apps and live scripts from sections 6.8 and 6.9 on the website, and here the core examples we're going to look at are these two: Laplace transforms with MATLAB and partial fractions with MATLAB. You'll notice there's a shorter, more focused live script in the tutorial folder. A reminder also that the purpose here of this video is not to teach MATLAB, but rather to illustrate quickly where the appropriate code is provided so that you can self-learn the syntax and experiment yourself in order to reinforce core concepts. So let's go to the MATLAB file then. So first of all, you'll see the file here we've got here, Laplace transforms with MATLAB. So you'll see section 1 first introduces you to symbolic variables to make sure you know what symbolic variables are. So you'll see a bit of code here, and on the right hand side you'll see what's happened. Two types of variables: variables which store numbers and variables which are symbolic. Once we've got that done with, we then move on to section 2, which you'll see at the top here. It says, right, we actually want to find the Laplace transform. So here's the definition, and how do we do that in code? And you'll see in the grey box down here a number of examples with the answers on the right hand side. So if x is e to the minus 2t, here's the Laplace transform, and here's the code over here for doing that. And you'll see there's 3 other examples: y, z and f. And as ever, what you can do is you can change these. So for example, instead of e to the minus 2t, I could say no, it wasn't e to the minus 2t, it was 0.43t. So I can change it. I can go up to the top, run section, and you'll see it's modified the right hand side accordingly. So you've got templates you can use. Similarly, if we look at section 3, this looks at inverse transforms. So you can see we've got this program here, iLaplace, which does the inverse transforms. And again, if you look over on the right hand side, you'll see that the solutions are given. So the inverse Laplace of x is xt, the inverse Laplace of y is yt, and so on down. Now you can, if you want, define a symbolic variable s and create your Laplace transform directly and then use iLaplace on that. So you'll see there's some examples here, and also a warning that actually MATLAB doesn't care what you use for the symbolic variable. When it does inverse Laplace, it just says what symbolic variable have you used, and I'm going to pretend that that's s. So some examples down there for you to play with. And again, a reminder, you can change these. So if I take this line 43, it wasn't a 0.4, it was 0.8. I've just changed it. If I now run section, and you'll see that k of t has been updated accordingly. Right, section 4 looks at how you can turn symbolic expressions into numbers, because obviously Laplace and iLaplace are using symbolic expressions, and you might want some numbers, and basically use this subs function. So there's an example here based on t squared to keep it simple so that you know what the answer is. So obviously 1 squared is 1, 2 squared is 4, and so on. You can see the answers over here, and hopefully that's enough to get you started. A slightly more complicated example is then given in these lines down here. Final values are a very important part that you might want to get from transforms. So you see some code here showing you how you might get the final value from a signal. And finally, in section 6, just for interest, you might want to compare solutions from Laplace and dsolve, which we did in the last 2 weeks. So you'll see here I've created a differential equation and said, how do I solve it using dsolve? And how do I solve it using Laplace? And then if we go over to the right hand side, we want to see, have we got the same answers? Now if you look at those carefully, apart from the formatting slightly different, you'll see they are the same. And there's some other examples lower down, and again you can experiment with these and change them. What about partial fractions? Well, partial fractions is a core skill for doing inverse Laplace, and you can see there's a typical partial fraction expansion given at the top just to get you started to illustrate what's going on. And then what this section shows, section 2, is how you can use MATLAB tools to get the partial fractions. So if you look at this top example, these lines down here, all right, you'll see if you had a transform 1 over s squared plus 3s plus 2, I happen to know the partial fraction expansion here, I can get those coefficients using this command here. And if you look on the right hand side, you see it tells me the residues, which are the numerator coefficients, and the poles. So I can actually get those coefficients using this residue file. There's another example here, slightly more complicated one. You can see it's given here. There's the actual answers, and you'll see with residues 3 and poles 3, it shows you that MATLAB will do it for you. Now section 3 and section 4 look at some more detailed things, just some MATLAB tools that you might find useful. How do you find the roots of a polynomial, or how do you create a polynomial from just the roots? So there's a few examples, and as ever you can change these if you want. Change the code, so I'm going to add an extra pole here, put a pole at 9, run section, and then I go over here and you can see there's my new polynomial. So, some conclusions. We've demonstrated some live scripts which allow students to develop an understanding of how to exploit MATLAB to compute and analyse Laplace transforms and transfer functions. They're not comprehensive, and slower videos and brief code snippets are provided on the main website in page chapter 6.